Hi all, today's topic is rings, the corresponding problem. The first question, find all zero divisors in a ring Z4 for a plus operation and dot operation. So if it is asked zero divisor means how we have to find means it is 4. So 4 means first we have to find the GCD. GCD for 4. So GCD of 1, 4 is nothing but 1. Then the GCD for 3, 4 is 1. So 1 and 3 are not a non-zero divisors. Okay, it is not a non-zero divisors. 2 you check. GCD of 2, 4, we know that it is 2 which is not equal to 1. If it is not equal to 1, whatever you get, that is a zero divisor. So 2 is a zero divisor. So zero divisor in a ring Z4 is nothing but only the 2. Same way, find all a zero divisor in a ring is at 8. Same way you have to check it. Okay, is at 8 when you check it 2, 4 and 6 you check it GCD. So all the GCD will be 2 which is not equal to 1. So the zero divisors are 2, 4 and 6. Remaining will be all the elements will be a non-zero divisors. The third question, show that is that plus operation and dot operation is a commutative ring with identity where the operation plus and dot are defined by plus it is defined by some rule and dot it is divided by some rule. So first we need to prove it is a commutative ring. So commutative ring means it should be a abelian. Okay, first one by one I will prove. First I will prove, first case I will prove for a plus operation. So we have to prove it's nothing but is at, so is at the ring. So which it is commutative ring? The commutative ring is nothing but R. So R plus operation is a abelian. We have to prove it first. So abelian means all the 5 conditions. So one by one we have to prove it. What are all the 5 conditions? Using the definition plus operation. So first closure property. Everyone know that closure property automatically satisfied because A it is given A plus B plus operation belongs to on a ring. Okay, so it is nothing but it belongs to a ring. So it belongs to on a ring. So it is nothing but plus operation is A plus B minus 1 also it belongs to on a ring. Closure property is satisfied. Second is associative property. So what is general associative? First I will write. We know that ABC is given in the question. ABC belongs to Z. So then we can write it as A plus B bracket plus C equal to A plus B plus C. So we'll change the bracket. So I'm going to prove this. So first I will take left hand side. So left hand side when I apply it A plus B as per the definition I have to use. So when I write it A plus B minus 1 plus operation C. So when I write it again, so when I write it A plus B, okay, so plus C, 1 already minus 1, now 1, so minus 2. So in your left hand side. Same way when I write it for right hand side, so A plus as it is. So B plus C I have to write B plus C minus 1. So when I again write A plus B plus C minus 2. So left equal to right. So associative satisfied. The third condition is identity element. So third condition what it is? A plus operation E is nothing but E plus operation A is nothing but A. So when by this is common definition. So when I write it as per the definition, it's A plus E minus 1. So when I write it this A plus E minus 1, it's equal to A. So as per the left cancellation or right cancellation, any one only you take it. So left cancellation law. So by left cancellation So by left cancellation law, E equal to 1. So the identity element is 1. So 1 is the identity element. 1 is the identity element for the plus operation. So same way next will be the identity element of the plus operation. Next will be the inverse. So inverse when I find it. So inverse. So what is our, we don't know which is the inverse. I will take generally B as a inverse element. Then I will check which I am getting as an inverse element. So when I take it, A plus B equal to B plus A equal to E. E is nothing but identity element 1. So when I write it, so when, as per the definition, A plus B minus 1 equal to 1. So when I write it, B equal to 2 minus A is the inverse. So it is nothing but inverse exists. So which is the inverse you have to find, and inverse exists we have to check. So all the 4 conditions checked. Last is the commutative. So commutative when I check it, so commutative I have to check it. Okay, commutative when I check it is nothing but A plus operation B equal to B plus A. I have to check it. I know that it's nothing but A plus B minus 1. So A plus B minus 1. So it's satisfied. So commutative exists. Okay. So for all the thing we have proved it for a plus operation. Now we need it to prove for a second case. We have to prove it for a dot operation. So dot operation we have to prove it. So I will use some other color. So for a dot operation I have to prove. So the dot operation what I'm going to have to prove. So now dot operation I have to prove. Second case I have to prove dot operation. So for that first condition I have to prove whether it is a what it is given commutative ring with identity. So I have to prove it is a first case I have to prove whether it's a closure property. So closure property I have to prove it. So now R dot operation I have to prove. So when I prove it, closure property everyone know it's satisfied. So it's nothing but A dot operation. So B is belongs to R. Then the corresponding whatever the elements as per the definition also it belongs to an R. Closure property satisfied. Second will be the associative. So associative when I satisfied. So dot operation I have to use. So A dot operation B dot operation C. Okay, bracket only changes. It's nothing but A dot operation B dot operation C. So as per our definition, A plus B minus AB into dot operation C. So it's nothing but A plus B plus C minus ABC. Okay, same way right hand side when I do it, A dot operation as it is, B plus C minus BC. Okay, so now A plus B plus C minus ABC. Okay, so minus ABC all 2 pair. So minus AB minus BC, correct? Minus here plus will become BC minus AC. Here also minus, when I write it, minus BC minus AC minus AB. So I am getting left equal to right. Check it, left equal to right. Therefore, associative also holds. Associative holds. Okay. So associative holds means I have to prove what I have to prove. Identity also I have to prove, then commutative if I proved, then it is completed. So first identity, commutative I will prove, commutative we have to prove. So commutative A dot B equal to B dot A. Okay. So when I prove it, so it's nothing but a plus b minus ab. So here a plus b minus ab, ba or ab or both are same only. So commutative also it is proved. Commutative holds. Okay. I have to prove identity. Last is the identity. So identity when I prove it. So identity when I prove it. So identity. So we know that generally A dot E is nothing but E dot A is nothing but A. So A plus E minus AE equal to E plus A minus AE equal to A. So you take only one side when I take it. Okay. So when I take E, I can take commonly outside. 1 minus A equal to A get cancelled. It becomes 0. So A cancel means it becomes 0 means so E equal to 0. A not equal to 0, E equal to 0. So commutative also proved. 0 is the identity element for dot operation. So everything we have proved. So now finally we can write. So E equal to 0 is the identity element. I am writing here green color. So it's the identity element for dot operation. Okay, so everything we have proved. So totally R plus operation and dot operation is a commutative ring with unity with identity element. Everything has a identity element. So completed. So one more question so that you can understand clearly. Prove that set of all ordered pairs A comma B of a real number is a commutative ring with a zero divisor plus and dot operation. Some rule has been given. So we needed to prove it. So now when I prove this, so what I have to prove? The same cases I have to prove. So it is we have to take first case we have to take. It is nothing but R plus operation I have to take. It is a abelian I have to prove it. So first abelian we have to prove it. First closure property. So the closure property, everyone know that closure property is nothing but A comma B and C comma D belongs to a ring. Okay, so everything we are doing under ring, G you should not write. So every element also it belongs means A plus C and B plus D also it belongs to a ring. So closure property is satisfied. Associative, second is associative. So associative when I do it, only the corresponding the procedure will change. Associative is nothing but A comma B and C comma D and E comma F. It belongs to some other element. Yes, I will write it. Then associative when I to write A comma B plus operation C comma D and plus operation and E comma F. Okay, so when I write it, so this is nothing but I have to write it A plus C, B plus D, okay, plus operation E and F. Okay, when I write it, again when I write it plus operation means I have to write it A plus C. So this both. So it is nothing but A plus C plus E. So it's E comma. So when I write it B plus D plus F. So written. It is LHS, left hand side only. Same way, right hand side when I do it, so it's nothing but A comma B plus operation, okay, bracket you see C comma D plus operation, E comma F plus operation, this both bracket, close this bracket. So when I write it A comma B as it is, plus operation, the answer you get it, it's nothing but C plus E comma D plus F. Okay, so when I write it, it's nothing but A plus C plus E comma B plus D plus F. You check it left and right are same. So associative satisfied. Plus operation is associative. Your own words. So associative. Okay, next will be after associative identity element. So identity when I prove it, I know that it is nothing but A comma B plus operation. So I have to write two elements E1 comma E2 equal to, when I write it, so A plus E1 and B plus E2. I have this same way E1 comma E2 plus operation under A comma B is E1 plus A comma E2 plus B. So it's nothing but both are equal to A comma B. So when I compare it with A comma B, so how can I write it means, so first element with respect to A. Okay. So it is A plus E1 equal to A. B plus E2 equal to B. So when I compare it, it's nothing but E1 only we have to calculate. E1 is 0, E2 is 0. So 0 comma 0 is the identity element. Is the identity elements. So next will be inverse. I have to find. I don't know which is the inverse. I will take some other element to be inverse. So inverse I don't know. So I'm taking C and D are the inverse. Okay, be the inverse element. Inverse of A comma B I will write it. When I write the definition, A comma B plus operation C comma D is nothing but E is nothing but 0 comma 0. When I write it as per the definition, I write means A plus C comma B plus D equal to 0 comma 0. So 0 comma 0 when I write it, A plus C equal to 0. So C equal to minus A. Same way B plus D equal to 0. So it's nothing but D equal to minus B. So the inverse are minus A comma B. Inverse is nothing but minus A comma minus B is the inverse. So completed. Commutative we have to prove. So last case is for commutative. So commutative we know that it's nothing but A comma B plus operation C comma D. When I write it, it's nothing but A plus C comma B plus D. Same way C comma D plus A comma B is nothing but same A plus C equal to B plus D. So therefore commutative holds. So all the cases we have proved for a plus operation. So it is a abelian. So R plus operation is a abelian. So is a abelian. Only plus operation. So dot operation still pending is there. So now we have to go with dot operation. So R dot operation is we have to check it. Is closed. First we have to check it. It's closed. We have to check means it's nothing but closure property. So closure property means we know that A comma B and C comma D closure property. So this is closure property. Okay, belongs to a ring. So then it is nothing but whatever the dot operation also, it is a closure property satisfied. So AC and VD also belongs to on a ring. So closure property satisfied. Second will be associative. So associative. So what is our formula? A comma B dot operation, C comma D dot operation, some E comma F dot operation. So bracket only changes first to bracket is equal to A comma B dot operation C comma D dot operation E comma F. So when I do it, so left, so it's nothing but AC comma BD dot operation E comma F. It's nothing but when I write it ACE comma BDF. Okay. So same way right hand side A comma B as it is when I write it. It's nothing but CD comma EF. Okay. So when I write it, it's ACE. Okay. ACE comma BDF. CE. This I have to change. It's nothing but CE. CE comma DF. Okay, now it's correct. Okay, both are same. So therefore associative also holds. Next will be a commutative. Associative exist or holds or it satisfied anything. Okay. So next will be commutative for a dot operation. So commutative is nothing but the same thing A comma B dot operation is nothing but C comma D dot operation is nothing but C comma D dot operation A comma B. So when I prove it, it's nothing but A C comma B D. So when I write it this A C comma B D. Okay, so both are equal. So commutative also exist for a dot operation. This exists for dot operation. Okay. So we have to prove it for a inverse. So what will be the inverse? So inverse when I prove it. So inverse I don't know which will be the inverse. Okay. So when I prove inverse. So inverse exists. So it is nothing but A comma 0 dot operation 0 comma B. Okay. So when I write it, it's nothing but when I write it A into 0 and then 0 into B is nothing but 0 0 only. So 0 0 is the inverse element. So 0 0 is the 0 0 is the this I will take it identity, then I will write. So identity is nothing but A comma B row dot operation identity I don't know. So 0 comma 0 when I write it, nothing but A dot 0 comma B dot 0 is nothing but 0 comma 0. So therefore 0 comma 0 is the identity element. Correct? Then only inverse. Inverse elements I don't know. So inverse elements I don't know. So therefore we know that so R ring plus operation and dot operation is a commutative ring with commutative ring only we have proved with identity only. So completed. Thank you.